about making sense of data, I actually added trusting, which wasn't in the original title, because I think these times actually it's very important also to think about can we trust the data we get. And I want to start first by thanking a lot of people that in my group that are working on these aspects of the research that I'm going to talk about here and funding agencies. And let me start by saying something that we all know about. It's we have a lot of data, and people talk about, between 85 to 95% of the data we have is in fact textual data. Books, newspapers, web, internet activity of different sorts, social network activity, and so on. So really a lot of data is textual data. And until, in the old times, maybe 10 years ago, we used to be able to be satisfied with databases. And if the data is in databases, we can actually do whatever we want with it. We know how to query a database, we know how to join, we know how to do a lot of things. When the data isn't in a database, it's unstructured, what we would like to do is actually to pretend that it is in a database. Essentially, to think about or to try to handle it as if it is in a database with an own schema. And this raises a lot of problems, from the simple problem of locating the relevant data to organizing it, accessing it, analyzing it, and synthesizing unstructured data. So, and really what you want to do when you deal with this kind of data, you want to deal both with the content and with the network. So who connects to whom, who talks to whom, who authors the data, and so on. So the research program that I'm going to hint about really aims at developing theories, algorithms, and tools that will allow us to transform raw data into useful and understandable information, and of course, as important is to integrate it with existing resources. So I want to talk very briefly about two aspects of this work. So the one that we talk about most of the time is this transformation from data to meaning, basically trying to figure out in automatic ways what does the document say. And I want to, at the end, hint a little bit about the research program that we started to develop over the last year or two that really aims at talking about, can we believe the data? What should we trust? Okay, so let me start with this kind of anecdote that all of us are familiar with. When you try to download a software package, or when you try to log in a hotel or any other place, you typically get this contract. Along with the contract come a question, do you accept? You never read the contract, you just say yes.
Yes.
But this is really doesn't make us happy. Right? Really what you would like to do is you would like to say, you know what, I want to make sure that this contract guarantees a few things that I care about. Don't give my email away. Don't do this, don't do this. So you'll be very satisfied if you can set in natural language 2 or 3 conditions, and someone, some program would read the contract and tell you, yes, they guarantee that. Or no, they don't. We don't do it. We don't have these programs yet, and it's difficult. In fact, we don't have this program only with a single contract. We actually have a lot of documents, a lot of text around that actually requires some level of understanding. So it's not only a deep level of understanding, something that requires us to know whether this contract is going to give our email away or not, but also it's massive because there's a lot of this. Why is this so difficult? So just to illustrate, so really we're talking about natural language. And when we talk about natural language, you can think about this as the bottom layer here. Above it is the level of meaning. And one of the 2 key difficulties are that, first of all, there's ambiguity. Whatever you say in natural language could have multiple meanings, depending on the context in which it's being said. And there's a second problem, which I call variability. When you want to express a meaning, there are many, many different ways you can express it. So these 2 issues together make the problem very difficult. Let me illustrate it with a couple of examples. So here's a very simple type of example. I call it context-sensitive paraphrasing. 3 sentences, they use the word title. Here is a list of synonyms taken from a dictionary for the word title. And I color-code it to map to the specific interpretation of the word title in these examples. And you can see that they vary a lot. In fact, you could even see antonyms in this list, because depending on the context, it could vary a lot. And this is a problem of ambiguity that we have to resolve. In fact, we resolve it unconsciously. We don't even think about it, but if you want to develop automatic tool, you have to address this. Variability is another problem. Say I want to know whether in a given document or a given document collection, it says that Jim Carpenter works for the government. There are many, many ways for us to say that. And they range from saying simply Jim Carpenter works for the US government to saying something like the Russian Interior Minister met yesterday with his US counterpart, Jim Carpenter. This also says that he works for the US government. So in order to address this variability, we can't just deal with this straightforward method, kind of Google-like keyword search. This method cannot deal with variability of expressing meaning, nor with ambiguity. We really need to dive deeper, understand relations expressed in text, understand entities, understand semantic classes. We need to bring knowledge from external resources because we use heavily knowledge whenever we read text and understand what it says. We should be able to integrate information across large collection of texts. We should be able to identify what's being said about an entity, about events, and so on. So there are many tasks, all they have to do with essentially resolving ambiguity and variability. What will we get if you can do this? I'm sure you can come up with your own examples. Of course, scientifically you care about this because it's going to allow us to move forward toward natural language understanding. But there are many, many interesting applications. Here are two simple applications. A law office is interested in getting a list of all the people they corresponded with in the last few days, years, or so. Even that is a difficult task because we don't know the names of the people. We can't just search. We just want to know, give me a list of all the people. And in fact, I want a little bit more. I want to be able to classify whether these people were mentioned in a good or a bad way in these documents. Simple task, not so easy to automate. Think about a training facility in a large lab or a corporation. They want to be able to provide new employees easy access to relevant information. So when they read material, they want to know what are the key concepts, what are the key entities, who's working on what applications, what methodologies were developed, and I want this to be mapped to the relevant projects and to some relevant information. Again, this requires pretty good level of processing the document. And here are two other examples. Scott is going to tell us a little bit later about the perspective of political scientists on this, but you can think about the stuff that Don was talking about before. Let's assume that we want to study climate change and its effect on societal stability or instability. It may require us to identify all events related to demonstration, protests, parades, analyze them at the level of who is participating, when does it happen, where does it happen, why does it happen, generate some kind of a timeline of events and a causality chain. And very relevant today, the notion of electronic health records. There's a huge amount of data in the medical domain that essentially today, that records a lot of information. Most of it is really narratives with a little bit of database elements inside it. And most of it is a write-only document. Physicians write a lot of information, no one can use it. But you could imagine there's a lot of applications, from medication selection and tracking to scientific gain that we could get if we could read this information and understand what it says. So as I said, it's a difficult problem, mostly because it has to address these ambiguity and variability problems, and conventional programs are not going to do the work in this case. So it's even difficult to program a simple predicate like, in a given sentence, is this word a verb or a noun? Think about it. Rather easy for any fourth grader, but it's not easy to write program because almost all the words in English can take multiple power speech shapes. And definitely this has become harder as you want to move up this shape. So all the work in this domain really is based on statistical machine learning and inference with kind of two research foci. So one has to do with modeling and developing learning algorithms for different phenomena. And I'm splitting it here to things that I call classification model, just determining a property of the text, which is something that I would say is well understood. Two structured models, where you can think about it as multivariate models, where we want to assign value to multiple variables at the same time, and these variables are interdependent. And to the issue of supervision. So one important secret, perhaps, in this domain is, yes, we have a lot of data. All of you can see that there's huge amounts of text out there. What we're lacking is supervision. In order to learn models, you really need someone to supervise the model and tell you what's the ground truth. What does it mean here? What does it mean there? And that's very expensive to get. So a lot of the work in this domain, in fact, struggles with how to develop learning protocols and algorithms that will deal with very weak indirect supervision. So that's one aspect of the work. And the second aspect is what I call inference, which is essentially decision making. Once I've learned models, we want to be able to incorporate into it some background knowledge, domain information, and together with these two, make some decisions. So really, the way you can think about this, you want to learn models, you want to acquire knowledge or constraints on these models, and together make decisions. This is the type of work that we're doing. So most of the rest of my talk is going to be examples, and I'm not going to give all the examples that I'd like to give. I want to give you some pointers. For example, if you go to my book's webpage, you will see a lot of demos that basically demonstrate a lot of the work on different aspects of the problem or different tasks in this problem, ranging from variations of semantic parsings to looking at temporal extraction, how to identify temporal expressions, normalize them, build timelines, looking at linking text to external resources like Wikipedia, co-reference, and so on. So there are many options. And I want to give a few quick examples. And the first one is going to be the simplest example we can give, which is dealing with entities. By entities, I mean, here's a piece of text. I want to identify these are the people, these are the locations, these are the organizations that are mentioned there. Even this problem that seems kind of simple is actually very difficult because entities are inherently ambiguous. JFK could be both a location or a person. And you want to be able to identify this, and the only way you have is using the context. So building long lists could help in some cases, but really isn't the solution, because if you look at any reasonable sized corpus, collection of documents, you will see that as the number of entities you see grows, the number of new entities that you see also grows. There are always new things, new names, new organizations, and so on. So you really need to use machine learning approaches, and many difficulties occur there, especially as you try to move from one domain to another. If you train model on newswire data, it's not going to behave well when you move up. Here's one simple example. When you can see here the word Wednesday. Wednesday used to be a day in the week. It's also a name of a soccer team. So we want to be able to identify it as an organization. What helps us here is the fact that somewhere else in the document we saw that there is an organization called Sheffield Wednesday, and probably they mean the same. But again, this requires learning and a level of reasoning in order to be able to do this. Things become even more complicated as you move to other domains. And I want to give an example from analyzing text in the medical domain. So these are discharge reports from hospitals that we look at. And in this case, it's the same problem. You want to identify concepts and entities, but the type of concepts and entities that you want to identify is completely different. So here, for example, I want to identify mentions in the text. This is how we call it. And then classify them to problems, treatments, tests, and people that are mentioned. Conceptually, the same problem that I mentioned before, but very different, and in fact requires a lot of background knowledge in order to solve. Actually, we want more than that. We want to be able not only to identify mention, but also to understand it at some level. I want to know, for example, that what's written here, stabbing left side chest pain, actually refers to the same thing that is written here as neuropathic pain. If I will not know that these are the same thing, these refer to the same thing, I will not understand what's happening and won't be able to support decisions the doctors make. So the decisions are actually hard. This is called the co-reference resolution problem, one of the most difficult problems we address. And of course, there are many other needs. I want to be able to do temporal recognition and reasoning. I want to deal with relations between problems, treatment, side effects, and so on. I want to deal with quantities and reasons about them, and so on. And you can imagine a lot of applications that this can have. In order to analyze text at this level, you really have to understand something about the semantic level of the text. And I'm going to give an example of something we call semantic role labeling, which is really a task of understanding text at the level of who does what to whom, when, and where. Here's an example that was generated, of course, for a DoD agency, a sentence about, a car bomb that exploded outside the US military base, killed 11 Iraqi citizens. We want to understand it at the level of, okay, there are two predicates here. There's an explosion, someone got killed. We want to know who are the arguments. So, a car bomb, the location in which it was happened, and who's the killer, who got killed, and so on. So this is the level of analysis that we want to be able to do. And this is a demo, again, for my group's webpage that shows what can be done. In fact, this isn't sufficient because relations in text are expressed not only using verbs. A lot of the relations are expressed using prepositions, nouns, and so on. And these are even more ambiguous than verbs. So for example, look at this simple sentence and look at the preposition. So someone died of pneumonia. So of represents a cause here. But you can represent a cause also with from, suffered from flu. But from can represent other things. In this case, from represents a location argument. And it could also represent kind of the start state. So again, it shows example for ambiguity and variability of expressing relations in text, and you want to be able to do this. And the same kind of model that I talked about before actually do it well here. Some of the difficulties, again, have to do with data. We don't have large amounts of data where people sat down and annotated. The of here represents a cause, the of here represents something else, the from here represents this. So we have to develop techniques that try to do these things in a semi-supervised way, and also to look at multiple phenomena to occur in the text and kind of constrain them against each other. Okay, I was going to talk a little bit about the math here, but I'm going to skip that. And I want to jump to two other examples. So one of the examples that we deal with is identifying events. Here are two very simple descriptions of events. I have an arrest event here, and I have a kill event here. Again, each one of these events could be expressed also in a whole paragraph, where it's a lot more difficult to identify. But we want to be able to identify events. We want to be able to identify causality between events. This happens because of that. We want to identify temporal argument. When did it happen? 2 days after Christmas is okay, but when is 2 days after Christmas? In order to be able to reason about it, I should be able to identify this temporal argument, but also to convert it to, December 27 relative, and maybe the year relative to some other place that mentions the year in this document. Otherwise, I won't be able to reason about this. Why do we want to do it? So this is a transition to Scott's lecture in a few minutes. We want to be able to support identifying events that happen. This is a collaboration that we have with the Client Center for Democracy, where they're looking at really quantitative political science. He's going to tell you a lot more about this, so this is just an example of how you can use this kind of natural language understanding in order to support other domains. So the final example that I want to give is something that I call the reference problem, that really you can think about in many respects as a way to extract or to acquire knowledge so as to support language understanding. So when you read documents, you can see that this is a document that mentions some Kennedys. Here's another document that mentions Kennedys. Here's yet another document that mentions Kennedys. You typically don't even remember how the name of a person was mentioned in the text, because you know that, the first and second document probably talk about this guy, and the last document talks about this guy. You actually ground it in some knowledge that you have, and this supports your disambiguation, and consequently also acquiring knowledge about this. How do we do this in text? You read about Chicago. Chicago means a lot of things. Chicago could mean font, it could mean a band, it could mean an album, and it could mean many, many other things, as we all know. Again, in order to understand what it means, we need to be able to ground it in something. We ground it in something that we know in the world, and in order to kind of simulate this and acquire knowledge, we actually have an effort that looks at text, tries to ground it also, and we're using Wikipedia for that. Wikipedia, as the world, allows us to ground things into it. Not so easy to do, but very powerful, because if you are able to do it and generate some kind of an information network between things that you read in text and Wikipedia, it gives you a lot of power. In fact, we can learn a very nice global model that identifies concepts, disambiguates them and grounds them into Wikipedia, and allows us to learn a lot of things about things that are mentioned in text. And as important is, we can train this model in a completely unsupervised way because we rely on links that people put into Wikipedia. Here are a couple of examples. So here is a blog that talks a little bit about the Israeli-Palestinian conflict, and you can see two names mentioned here, Mahmoud Abbas and Abu Mazen. Some of you that maybe know something about this conflict would know that this is the same person. But the writer of the blog used these words and didn't reveal that this is the same person. So he knew, and he assumed that the readers do, but if you don't know, the context here will not let it do it. So our model, though, you can see points Mahmoud Abbas to Mahmoud Abbas webpage, and Abu Mazen also to Mahmoud Abbas. So basically, our model figured out that it has to be the same person, given the context of other pages that are pointed to from this page. So it not only identifies concepts that are important, but also disambiguates and maps them correctly. Here's an application of this in the medical domain. So again, when I started to work on these electronic health records, I can tell you, even now, in fact, I don't understand a word of what they're saying. I mean, all this terminology is too complicated for me. However, using the Wikifier, I can actually look at prototype here, or bone metastasis, and I can run the Wikifier, and it turns out that it points this to bone tumor. So the surface representation doesn't matter so much. It figured out that the corresponding page is actually bone tumor. If you go and read it, you'll see that this is right. So really, the significance of this is not only that we can identify important concepts in text, important entities, and disambiguate them and learn something about it. I think that this is actually something that can be useful as a tool for scientific literature and even for educational application. Okay, so that's basically ends what I wanted to say, and I want to spend 2 minutes on another aspect of this work that I think is really important and really has some societal significance. So, you know, we already know and said that there's a lot of information out there, but it's of uncertain quality. And the quality deteriorates as the amount of information out there and the competition on being first to reveal something grows. And we all know, you know, the Boston events just recently, and just with this event, I can fill up a lot of slides of examples of what has happened and how come we cannot count on anything that happened. But basically, a lot of stories went out, and the relation to the facts were, you know, very, very weak. So the question is that of distributed trust. There's a lot of data sources that give us information about things. And sometimes by mistake and sometimes for a reason, they don't give us the right information. One of my favorite examples here is the story of Senator Kyle, who 2 years ago stood on the Senator floor and said something like, well over 90% of what Planned Parenthood does is supporting abortion. The truth is 3%. But you know, it's a reliable resource, kind of, and it's already there in the transcript of the Senate, so is that the truth? So we really need to be able to develop some kind of a computational trust system that will be our proxy, and maybe will be a proxy between text and some other systems, question answering system, navigation systems, news aggregation systems, warning systems and so on, something that will take a lot of information, figure out what's true and what isn't, and tell us something about it. And you know, another favorite example of mine is the medical domain. There are thousands of support groups, media forums, and so on, and really hundreds of thousands of people get the medical information from the internet. They search for the best treatment for his side effect for and so on. But some of the users on these news groups actually have an agenda, pharmaceutical companies, for example. So the question is, to what extent we can believe what we read there. So the goal of this research, and by the way, this problem isn't easy even for people. And again, I have a lot of examples, and I'll just stop on this one from the recent Supreme Court decision on approving Obamacare. If you remember, at the first few minutes, or more than minutes, after this came out, people misinterpreted it. So it's not so easy. So the research program that I'm talking about is a research program that attempts to look at sources and claims they're making, and try to be able to score trustworthiness of claims and sources. So think about it as developing the ability to generate a probability distribution over trustworthiness of sources, along with a distribution over the credibility of the claims they're making. And we are dealing with basically developing the algorithmic tools that will allow us to do something like this. So again, I don't have time to talk about the content of this research direction, but I think it's clear that we need something like this. It's clear that it's very difficult, and we've been dealing over the last couple of years with trying to develop some algorithmic tools to support that. And with this, I'm going to end. Hopefully, I gave you some idea of what's happening in this area, what are the difficulties, and some of the progress that we've started to make. Thank you.
Questions?
Very nice talk, very inspirational. Just a curiosity. For example, in your talk you mentioned that JFK would be a person or a location. So would be Dallas, for example. I will use Dallas just to make my point. For example, today, if the word Dallas appears in almost independently of a context, is very much likely to be a location because of the George W. Bush inauguration, the library inauguration in Dallas, Texas, right?
Today.
Yes. Then that's the question I wanted to ask you. The present context, does it come into the picture of what you are?
Yeah, very good question. Of course. So you could say, even generalizing what you say, if you start reading a document and you see the word Dallas, and in the beginning you think that it's a location, it's very likely that later on in this document, other occurrences of Dallas will also be locations, right? And you are generalizing it, you know, today, Dallas is more likely to be a location. Of course, we are using this. So this is what I call structured prediction problems, where you have to make decisions with respect to many things, and they are not interdependent, they are not independent. Right? So if I've seen Dallas, and it's today, and I know that there is an inauguration of something in Dallas, I have to take this into account, and this is going to change something about the probability my models should assign to occurrences of Dallas. And this happens all the time. You know, the sense of a word. So the word table could mean many things, right? It could be also a noun, it could be a verb. But in a given context, if I see table and I think, well, this is probably a noun here, it's very likely that in the same context or in the same document, it's also going to be noun and mean the same thing. So we are using these things, of course, but try to learn this automatically from text. Thank you.
What's a comfortable data size that you'd like to use to have a nice prediction?
Okay, that's a very important question, and it varies over tasks. So, for example, in order to train entities identifier, this is kind of one of the easier problems today. So, with a couple hundred documents, couple hundred examples, you can already develop a solid model. But if you want to do semantic parsing that involves multiple decisions with respect to each sentence and a lot of interaction between them, you probably want to have thousands of examples. So it really varies on the complexity of the problem.
So you talked about ambiguity within English, right? What about ambiguity as you go from one language to another language?
Yeah, okay, so that's again a very, very important question that intensifies the issue of availability of data. So most of these tools have been developed in English, and the reason is we have a lot of data. So people collected corpora and annotated corpora. In many other languages, we don't have a lot of corpora. There's a lot of effort first to annotate data in other languages and also to develop techniques that allow us to use what we call sort of weakly parallel corpora in order to transfer abilities of analyzing English to something else. So as an example, I can take the BBC, and BBC has news in Russian, in English, in many other languages, and I could assume that if it's today, about the same international news are going to be covered in the Russian BBC and in the English BBC. So this will allow me to use models that were trained for English and map the predictions to the Russian text and try to improve models for Russian, for example. And I mean, there's a lot of research on trying to do these things, basically to bridge over the fact that in most languages we have no resources. Yeah, very important direction.
Right. So there's time